Thank you to the organizers for inviting me. I think that it's late for you, but it's early in the morning for me, or late-ish afternoon anyway.
3 o'clock.
Okay. All right. So I want to play a game. Oh, and I want to say this is joint with Colin DeFont and Eric Hansen. And I want to play a game with you. So everything in the talk will be centered around a sort of small running example. We're going to take a type A Dinkin diagram like A3 and then put arrows between the nodes in both directions and kill all of the 3 cycles. So this notation probably isn't very helpful, but I'm going to show you a better picture in the next slide. Okay, so there's the quiver right down here. So I have my 1, 2, and 3 for A3, and then arrows in both directions, and I'm killing all of the 2 cycles. And then on the board, I drew the AR quiver for this. So it kind of wraps around on itself. You notice the simples 1 and 3 are on both sides. Okay, so we're going to play a game with torsion classes. And I think, yes, good. That's my next slide. So here's the lattice of torsion classes. In case you're not familiar, torsion classes are collections of modules which are closed under taking extensions and quotients. So I've collected all of them for our small example, and I've ordered them by containment. So as you're moving up the page, you're adding more and more modules. And at the very bottom, we've got the smallest guy. And we want to play a game where we're going to take a torsion class and we're going to define a function which moves us down in this poset. Okay. And the example I'm going to focus on, I'm sorry if the numbers are a little small for you. I hope your screens at home are bigger than mine. The example I'm going to focus on is this guy right here. It's just below the top. It has the simples 1 and 3. It has the injective at 2 and projectives at 1 and at 3, and then these extra 2 guys. Okay. So to do this game, which is called pop stack sorting, I need a little extra data about my torsion class. I'm going to use the brick labeling, which just because this talk is sort of short, I didn't put all the references, but this was sort of discovered around the same time by a couple of different people. I call this the brick labeling for the torsion classes. What we're going to do is we're going to take every edge in the picture from the previous slide. So that's a relation between 2 torsion classes called a cover relation. And it's just saying that in the text here, this torsion class is contained in T prime, and there's no other torsion classes between them. Okay, and we're going to label that edge by a module, which happens to be a brick. It's S here, so that when you add S to the smaller torsion class and close under extensions, you get this like 1 step bigger guy. And you can extend this to labeling cover relations down, but if you want, just focus on thinking about like moving up, so sort of growing your torsion class. Okay, so let me show you what this looks like in our running example. So I did all of the hard work for us. You can imagine from the very bottom as I go up, I have the torsion class, which just has 1 or like additive closure of that. And how would I get that from the very bottom? Well, I just add the simple at 1. And then moving up is not so hard. Like here, I would add this module 1, 2. So I'm going to label that. This torsion class, which has the simple at 1 and 2, and this 1, 2, and 2, 1 is maybe slightly more complicated. The cover relations going down below it are both the simple at 1 and at 2. And that's because, for example, here, when I add the 2 to this torsion class and close under extensions, I get this other torsion class, which has 2 above 1. Okay, so you don't have to absorb all of that. If you want, you can just say it's been done for me. We have this labeling of the cover relations. And I'm going to take, again, this torsion class sort of towards the top. And I'm going to keep track of the cover relations going down and the labels there. And the label is the module with 3 above 2 and 1 above 2. Okay, so here's what my function is, this pop stack sorting. Just to make the notation a little easier, those labels going down, I'm going to call them D for down. And all I'm going to do is I'm going to take my torsion class and I'm going to intersect with the left perp of D. So I look at all the modules that don't map to those down labels. And then I intersect with T. Okay. And then I'm claiming that that takes you down in this post set. So let's do a small example just to get a feel for how this game works. And it's a little easier actually to do this with the AR quiver because you can keep track of like who maps to who. So I took that torsion class that I described before. It has the simple at 1 and 3, injective at 2, projective at 1, projective at 3, and these two other guys. Those two other guys were our down labels, right? So in yellow, I highlighted this torsion class in the R quiver. And then here are the down labels. And what this pop stack sorting does is it says, okay, in the torsion class, take all of the things that don't map to those down labels. And I think in the AR quiver, you can see, well, I have to throw out the projective at 1, the projective at 3, and then the down labels themselves. And that leaves me with what's boxed off in blue. So that's the image of pop. And it is a smaller torsion class. And the idea here is you're doing something called sorting. So in the context of torsion classes, what this means, this actually comes from some computer science thing. But what this means for us is we want to eventually get from whatever torsion class we started with to the very smallest torsion class. So let's just do it again. In this smaller torsion class, which now has the injective at 2 and the simples at 1 and 3, I find the down label, which I circled in red for you, and it's that injective guy. And again, I say, okay, take all the things in my torsion class that don't map to this. And that's just the simple at 3 and at 1, and this is boxed off in pink. And let's just keep playing. Okay, so the down labels here are actually just the simples at 1 and 3. So when I do this like intersect with the left perp, now finally I have the smallest torsion class and I'm fully sorted. When you're doing dynamics like this, as a combinatorialist, I think a lot about counting questions like how long did it take me to get sorted? What things take the longest? How many are there? What things are in the image of this map? Those are the types of questions I'm interested in. Maybe let's do one more example. I think I have time for that. Oh, skipped. Here we go. Yeah. So this torsion class has 3 things. It's kind of generated by the projective at 1. And that projective at 1 is also the down label. And I think if you kind of run through my work here, hopefully looking at the AR quiver, this also looks about right. The left perp of the projective at 1 intersected with T just leaves the other 2 bricks, the other 2 modules here, do the same thing again. You're going to kind of cut off that 1 above 2, leaving the simple at 1. And finally, that goes away too. This also took 3 iterations to be fully sorted. In this whole poset, what are we looking at? We're looking at the image of this pop stack sorting method that I've described. So in the first example, I started with this guy. And when you apply this pop stack sorting, remember, you just cut off the down labels, but also the projective at 1 and at 3, and that sends you to this guy circled in blue. So that's how this one ends up in the image. Okay, so what my co-authors and I, one of the things that we were thinking of is there a nice description of the image of the pop stack sorting method for tau tilting finite algebras? And we were not able to answer that question, but it turns out for hereditary algebras, this does have a really nice description. So a torsion class is in the image of this pop stack sorting method if and only if there are no extensions between any of those down labels, those modules in the set D, and there's no projective contained in your torsion class. It turns out that this theorem doesn't hold for the algebra that's been my running example, but this algebra in the running example, the images had been also already studied. But I guess that leaves, I mean, really, I wanted to give this talk to show you that there's actually just a ton of open questions here. I mean, what is the image in general for a tau tilting finite algebra? Do you have a favorite tau tilting finite algebra where you could study the lattice of torsion classes and just play this game? Could you find an upper bound for the number of times it takes to sort things? And then I like counting, so I put a counting question here. Okay, I think that takes me to the end. Thank you for listening.